In the previous lectures, we discussed the Big M method to solve the maximization and minimization models. In the present video, we will discuss the another example problem on the Big M method. Let's see the problem. Show how the Big M method will conclude that the following problem has no feasible solution. Problem is maximize z equal to 2x1 plus 5x2 subject to the constraint 3x1 plus 2x2 greater than or equal to 6, 2x1 plus x2 less than or equal to 2 and x1 and x2 are the greater than or equal to the 0. While solving the Big M method, all zj minus cj values are positive and artificial variable is not removed in the basis, then given problem is not having the feasible solution. Let's see the solution. First step is convert the general linear programming problem into standard linear programming problem. For this, first we have to observe the constraint, and if the constraint is having the less than or equal to inequality symbol, then we have to introduce the positive slack variable. And if the constraint is having the greater than or equal to inequality symbol, then we have to introduce the negative surplus variable and also artificial variable. And if the constraint is having the equal to symbol, then we have to introduce only positive artificial variable, that is plus a. In the given constraint, first constraint is having the greater than or equal to inequality symbol, then we have to introduce the negative surplus variable as well as positive artificial variable. So we have to introduce the surplus variable S1 and also artificial variable A1 in the first constraint. Similarly, we have to observe the second constraint. In the second constraint, inequality symbol is less than or equal to inequality symbol. Then we have to introduce the positive slack variable. So in the second constraint, we have to introduce the positive slack variable, that is S2 in the second constraint. Then given constraints will become the 3x1 plus 2x2 minus S1 plus A1 equal to 6. Second constraint is the 2x1 plus x2 plus s2 equal to 2. So moreover, we have to reformulate the given objective function in the terms of decision variables, slack variables, surplus variables and artificial variables. Then objective function will become the z equal to 2x1 plus 5x2 plus 0s1 plus 0s2 minus a1. Here cost coefficients for slack variable and surplus variables are the 0 and cost coefficient for the artificial variable is the minus m, and x1, x2, s1, s2, a1 all are the positive values, which means greater than or equal to the 0. Second step is find the initial basic feasible solution. For this, assume the all basic variables, that is x1 and x2, and surplus variables, that is s1, are considering the 0 and substitute in constraint equations. So we have to consider the x1, x2 and s1 equal to the 0 and substitute in the constraint equations. Then we will get the artificial variable a1 and slack variable s2 value. So here x1, x2 and s1 is the 0, then a1 value is the 6 and x1, x2 are the 0, then s2 value is the 2. Next step is construct the initial simplex table. This is the initial simplex table. Here B is the basis variables, that is A1 and S2. CB is the cost coefficients. Here A1 cost coefficient is the minus M, S2 cost coefficient is the 0. XB is the initial basic feasible solution, that is for A1 it is the 6 and for the S2 it is the 2. And these values are the coefficients of the variables and obtained from the constraint equations, that is x1 coefficient is the 3 and x2 coefficient is the 2 and s1 coefficient is the -1, and in the first constraint there is no s2, so here s2 value is the 0 and a1 coefficient is the 1. Similarly observe the second constraint equation. Here x1 coefficient is the 2, x2 coefficient is the 1 and here there is no s1, so its coefficient is the 0 and s2 coefficient is the 1 and here there is no a1, so its coefficient is the 0. And Cj is the cost coefficients. For the x1 variable cost coefficient is the 2 and for the x2 it is 5 and for the s1 it is the 0 and for the s2 it is the 0 and for the a1 it is the -m. So next step is calculate the values of Zj minus Cj and check the basic feasible solution for the optimality. So in this step 4, first condition is if all the Zj minus Cj values are greater than or equal to 0, the optimal solution will be obtained. Second condition is if at least one Zj minus Cj is the negative, then indicate by arrow and this column is called as the key column. And if the more than one Zj minus Cj is the negative, then choose the most negative of them and thus column is called as the key column. So first we have to calculate the Zj minus Cj values. Zj minus Cj equal to Cbj into Xj minus Cj. So first we have to calculate the Zj minus Cj for the first variable. So that is the Z1 minus C1 equal to CBX1 minus C1. So it is the CBX1 will become the 3 into minus m plus 2 into 0 minus C1 is the minus 2. So its value will become the minus 3m minus 2. Next we have to calculate the Z2 minus C2 for the second variable. So it is the CBX2 minus C2. So CBX2 is the 2 into minus m plus 1 into 0 minus 5. So its value will become the minus 2m minus 5. Next we have to calculate the Z3 minus C3 for the third variable, that is the CBX3 minus C3. So CBX3 will become the minus m into minus 1 plus 0 into 0 minus 0. Its value is the m. So next Z4 minus C4 for the fourth variable. So that is the CBX4 minus C4. CBX4 will become the minus m into 0 plus 0 into 1 minus 0. So its value is the 0. So next we have to calculate the Z5 minus C5 for the fifth variable. So that is the minus m into 1 plus 0 into 0 minus of minus m. Its value is the 0. So here Zj minus Cj values are the minus 3m minus 2, minus 2m minus 5, m, 0 and 0. Then observe the conditions in the step 4. So here we are getting the more than one Zj minus Cj values are the negative values, that is minus 3m minus 2, minus 2m minus 5. These two are the negative values. So here we are getting the more than the one Zj minus Cj value is negative. Then among these values we have to choose the most negative value, that is minus 3m minus 2. So this is for the x1 column. So this is we are calling as the incoming vector. So here x1 column is the key column and calling as the incoming vector. So x1 variable enters into the basis. So next we have to determine the outgoing variable from the basis. Next step is calculate the minimum ratio of xb2 coefficient in key column or incoming variable, that is xb divided by ck, and ck value should be the greater than the 0, and here ck values are considering the x1 variable coefficients. So here first we have to calculate the xb divided by ck for the first row, that is the for a1 row. So for the a1 row xb value is the 6 and incoming variable coefficient is the 3. So 6 by 3 equal to 2. So next minimum ratio of xb divided by incoming variable for the second row, that is for the S2 row. So here xb value is the 2 and incoming variable coefficient also 2. So it is the 2 by 2 equal to the 1. So here minimum ratio is the 1 and it is indicated by arrow, and S2 is outgoing vector, which means S2 is leaves from the basis. So here S2 is the outgoing vector. So next we have to identify the key element, so which is the common element in the key row as well as the key column. Here key row is the S2 row and key column is the x1 variable column. So among this row and column, so common element is the 2. So 2 is the key element. So next step is construct the new simplex table by entering the incoming variable. This is the new simplex table, and here we are replacing the outgoing variable S2 with incoming variable x1, and its coefficient value is the 2 in the basis. Next we are applying the following row operations to get the new simplex table. And before applying the row operations, remember we have to get the 1 at the key element position in the key column, and remaining values in the key column should be the 0. So for this we have to do the following row operations, and here consider the R1 old and R2 old are the row 1 and row 2 in the old simplex table, and R1 new and R2 new are the row 1 and row 2 in the new simplex table. So first row operation is the R2 new equal to R2 old divided by key element. Here key element is the 2. So R2 new equal to R2 old divided by 2. So here R2 old elements are the 2, 2, 1, 0, 1, 0. Then R2 new elements are the 2 by 2, it is the 1, 2 by 2, 1. So 1 by 2, 1 by 2, 0 by 2, 0, 1 by 2, 1 by 2, 0 by 2, 0. So enter these values in the new simplex table. Next row operation is the R1 new equal to R2 old minus 3 R2 new. So here R1 old elements are the 6, 3, 2, minus 1, 0 and the 1. and R2 new elements are the 1, 1, 1 by 2, 0, 1 by 2, 0. And 3 R2 new will become the, so 1 into 3 it is the 3, 1 into 3 it is 3, 1 by 2 into 3 it is 3 by 2, 0 into 3 it is the 0, 1 by 2 into 3 it is the 3 by 2, 0 into 3 it is the 0. So next we have to perform the row operation is R1 old minus 3 R2 new, that is 6 minus 3 it is the 3. So enter in the new simplex table. So next to 3 minus 3 it is the 0, and 2 minus 3 by 2 it is the, so 1 by 2. Next to minus 1, 0, minus 1 minus 0 it is the minus 1. 0 minus 3 by 2 it is the minus 3 by 2. 1 minus 0 it is the 1. So enter these values in the new simplex table. So now this is the new simplex table. Next we calculate the Zj minus Cj values to check the basic feasible solution for the optimality. So how to determine the Zj minus Cj values for the new simplex table, that is the first iteration simplex table. So here first we have to determine the Z1 minus C1. So Z1 minus C1 value is the 0 into minus m plus 1 into 2 minus 2. Its value is the 0. Next to Z2 minus C2 is the 1 by 2 into minus m plus 1 by 2 into 2 minus 5, and this value is the minus m by 2 minus 4. So next Z3 minus C3 value is the minus 1 into minus m plus 0 into 2 minus 0, and this value is the m. So next is the Z4 minus C4. It is the minus 3 by 2 into minus m plus 1 by 2 into 2 minus 0, and its value is the 3m by 2 plus 1. Next Z5 minus C5. This value is the 1 into minus 1 plus 0 into 2 minus of minus m, and this value is the 0. So here observe the Zj minus Cj values are the 0, minus m by 2 minus 4 plus m, 3m by 2 plus 1 and 0. Here we are getting the only one negative Zj minus Cj value for x2 column. So here we are considering the x2 column is the incoming vector. So here x2 column is the key column and it is calling as the incoming vector, and x2 variable enters the basis. So next we have to determine the minimum ratio of xb divided by incoming variable. So first we have to calculate the for the first row, that is the for the A1 row. For the A1 row, xb value is the 3 and incoming variable value is the 1 by 2. So it is the 3 divided by 1 by 2, it is 3 into 2 is 6. Next we have to determine the minimum ratio of xb divided by incoming variable for the x1 row. So here xb value is the 1 and incoming variable value is the 1 by 2. So 1 divided by 1 by 2, it is the 2. So here minimum value is the 2 and it is indicated by the arrow, and x1 is the outgoing vector. So basic variable x1 is leaves the basis. Next we have to identify the common element in the key row as well as the key column. Here common element is the 1 by 2. So 1 by 2 is the key element. So next step is once again we have to construct the new simplex table by entering this incoming variable. This is the second iteration simplex table, that is the new simplex table. So here we are replacing the outgoing variable, that is x1, with the incoming variable x2 in the basis, and moreover its cost coefficient value is the 5, so enter the 5 value in the CB column. So next we have to perform the following row operation to get the new simplex table. First row operation is the R2 new equal to R2 old divided by key element. Here key element is the 1 by 2. So this can be, we can be written as R2 new equal to R2 old into 2. So these are the R2 old elements. Then this is, you have to multiply with the 2 and substitute these values in the second row of the second iteration simplex table. So R2 new values will become the 1 into 2, 2, 1 into 2, it is the 2, and 1 by 2 into 2, 1, 0 into 2, it is the 0, 1 by 2 into 2, it is the 1, 0 into 2, it is the 0. So next row operation is R1 new equal to R1 volt minus 1 by 2 into R2 new. So first we have to observe the R1 old elements. So R1 old elements are the 3, 0, 1 by 2, minus 1, minus 3 by 2 and 1. R1, so R2 new elements are the 2, 2, 1, 0, 1, 0. So next one we have to do the R2 new divided by 2. So which will become the 2 by 2 it is 1, 2 by 2 it is 1, 1 by 2 it is the 1 by 2, 0 by 2 it is 0, 1 by 2 it is 1 by 2, 0 by 2 it is the 0. We have to do the row operation is R1 old minus R2 new divided by 2, which will become the 3 minus 1, 2, and 0 minus 1, minus 1, and 1 by 2 minus 1 by 2, it is the 0. So minus 1 minus 0, it is the minus 1. So minus 3 by 2 minus 1 by 2, it is the minus 2. 1 minus 0, it is the 1. Substitute these values in the R1 new. So next once again I have to calculate the Zj minus Cj values for the second iteration simplex table. So first I have to calculate the Z1 minus C1. It is the minus m into minus 1 plus 5 into 2 minus 2. It is the m plus 8. So next Z2 minus C2 is the minus m into 0 plus 5 into 1 minus 5. This value is the 0. And next one is the Z3 minus C3. It is the minus m into minus 1 plus 5 into 0 minus 0. It is the m. So next Z4 minus C4 value is the minus m into minus 2 plus 5 into 1 minus 0. Its value is the 2m plus 5. So next one is the Z5 minus C5 value is the minus m into 1 plus 5 into 0 minus of minus m, it is the 0. So here observe the all the Zj minus Cj values are the positive, and all Zj minus Cj values are the positive, but we have to observe here, so artificial variable, that is a1, is not removed in the basis. So here we are getting the all Zj minus Cj values are the positive, but artificial variable is not removed in the basis. So in this situation we are calling as the given problem is not having the feasible solution. So this is the solution, and thank you.